Hello, my name is Ashik Nagidigiri Harish and my project is filtering out spam emails using the naive Bayes, KNN and SVM classifiers. These are the topics that are going to be covered in this presentation. First and foremost, let us look as to the motivation as to why a spam filter is required. As you know, electronic mail or email is one of the most popular means of communication in today's generation. This is because of its high speed of communication and its relative ease of using. Thus, it has become a target for manufacturers who want to constantly advertise and promote their products by sending out these emails to consumers. As you know, the users are not interested in such type of emails and they are very much hassled when they see their inbox filled out with such type of spam emails. Hence, there is a great necessary to filter out these spam emails and hence a spam filter is very much necessary in email. Let us look as to how I have gone about with this project. The overlaying concept is to build an email filter which can effectively recognize these spam filters with very high accuracy. The first step is the creation of the feature vector, which is nothing but the frequency of the words that occur in both the spam and ham across both the training and the testing dataset. Using these features, I went on to train the naive Bayes, SVM, that is both the linear and the non-linear type, and the KNN classifiers, which were the classifiers used in this project. Next, using the trained model, I use it to predict the incoming new dataset, and with the obtained results, I compare the performance for the various sizes of the dataset. By various sizes of the dataset, I mean for different sizes of the training dataset, and then I have tabulated the results. The project can very well be extended to classify images as well. Now, let us look at the dataset that I have used. It is called the link spam dataset and it consists of 960 emails in total. The distribution of the dataset will be explained in the next slide. Here, I have used a preprocessed link spam dataset. What the preprocessed dataset has done is that it has removed the stop words like and, of, is, the, and in addition to that, it has also removed punctuations and numbers which are irrelevant in the spam filter. Next, I have also reduced the different forms of words such as write, writes and written, for example, to a single form such as write. And all these words have also been converted to lower cases. This does not affect the performance. As you know, in the naive Bayes, the features are independent of each other, and also for SVM and KNN, the performance does not degrade by reducing all different forms of words to a single form. This is the distribution of the link spam dataset. As you can see, it consists of 350 ham and 350 spam emails in the training emails. Here, ham refers to the genuine emails. And in the testing emails, we have 130 ham and 130 spam for a total of 260 emails. And thus, in general, in total, we have 960 emails. 480 of them are ham and 480 of them are spam. Here, the ham and spam are equally distributed across both the training and the testing email dataset. Let us look at as to how I have done the feature extraction. The first and foremost step is the creation of the dictionary. The dictionary is nothing but the words contained in the entire dataset, that is including the training and testing, and also we need to keep track of the number of times these words occur. And based on the number of times these occur, that is the count, the words are then arranged in descending order, which ultimately gives us the dictionary. Then the features are generated and stored in a .mat file. Here the features consist of the file ID in the first column, word ID in the second, and the frequency, the number of words that occur in that email alone. Here the feature set is created once for the testing set and once for the training set. Here I'll go on to talk more about how the feature set looks like in the next slide. Furthermore, the feature set will be used to create the training matrix for the classifiers. This is how the extracted features look like. As you can see on the right hand side, the first column is the file ID referring to the file itself. So here file ID 1 has word ID 4, word ID 3 and word ID 65. Here word ID 4 is repeated 13 times, word ID 3 is repeated 1 time and word ID 65 is repeated 2 times in that particular email alone. Here the word ID is generated by comparing it with the index in the dictionary. So word ID 4 refers to the fourth index in the dictionary, that is the word language. Hence, it effectively means in the first email, the word language is repeated 13 times. In the first email, for the index 3, the word order is repeated 1 time, and so on. This is created, as I mentioned before, for both the training and the testing set. Now, let us look at some background on the classifiers. As you can see, the naive Bayes classifier is based on the popular Bayes theorem. Bayes theorem states that if you know the outcome of a particular event, then you can calculate the probability of the sequence of events that have led to that particular event. Here, the naive Bayes classifier extends it by stating that if the features are conditionally independent of each other, which is the assumption that we have made here, then under joint probability, the equation can be further rewritten as the one you can see in the second one. Next, let us look at the k nearest neighbor classifier. Here, this is one of the most popular classifiers used to perform basic recognition problems and is based on the non-parametric method. Here, when a new input data is fed to the classifier, it finds its k nearest neighbors. Here, k is the number of neighbors specified by the user himself. On looking at the k nearest neighbors, it measures the distance in terms of a specific distance metric. The distance metric may be Euclidean, Hamming, Chebyshev, or whatever the user specifies. Then, after finding out the distance, it classifies it to a particular label based on the label which the majority of its neighbors possess. Here, the choice of k plays a very important role. As the value of k increases, the noise decreases, but at the same time there is a disadvantage of the class boundaries becoming less and less distinct. For text-based classification, it has been found out that k is equal to 1 gives us the best result. The third classifier here used is a support vector machine, which is a popular machine learning algorithm used. It is a supervised learning model. As you can see from the diagram, you can see that the input feature points, that is the red and the blue points, are non-linearly separable in the lower dimension. However, when conversion to a higher dimensional space, you can see that using a hyperplane, they can be linearly separated, and this is the fundamental concept behind the working of a support vector machine. So, let us look at the results that I have obtained using all these three classifiers. For the naive Bayes classifier, as you can see, the number of emails wrongly classified is very much less, and the percentage hovers around 2.5%, which is very effective given that it is a very simple classifier. As you can see, increasing the number of training emails from 100 to 700 did not change the performance of the naive Bayes classifier to a great extent, and the accuracy almost remains the same throughout. Let us look at the result for the linear SVM classifier. The linear SVM classifier performs poorly when the number of training emails is limited, but as you increase the number of training emails, its performance is almost equal to that of the naive Bayes classifier. As you can see, there is a drop in the percentage of emails wrongly classified from 9.23% to 2.69%. Let us look at how the nonlinear SVM classifier behaves. As you can see clearly from the results, the nonlinear SVM classifier is not an effective way to classify text-based classification. It performs very poorly and gives you almost 50% error rate, which is highly unsatisfactory for creating a spam filter. The last classifier used is the KNN classifier. The KNN classifier performs poorly but much better than the nonlinear SVM, but in comparison to the linear SVM and the naive Bayes classifier, its performance is a bit on the downside. As you can see, it's the same case as the linear SVM, where increasing the number of training emails improved its performance. For 100 training emails, it gave us a percentage of wrongly classified emails as 21%, which dropped to 7% when it was increased to 700. These are the graphs that were obtained. As you can see, the one on the left hand side has number of training samples on the x-axis and the percentage of males that were wrongly classified on the y-axis. As you can see, the SVM nonlinear classifier performs very poorly and it is indicated by the yellow line, while the blue line, which indicates the naive Bayes classifier, is at the very bottom, which shows that for irregardless of the number of training samples, the percentage of males wrongly classified is always low, while for the SVM linear and KNN, increasing the number of training samples decreased the percentage of males wrongly classified. The next on the right hand side was the time complexity of various classifiers. I wanted to know how much time these classifiers took to classify these emails for the different amount of training samples used. That is, the time is the total time taken to classify emails based on 100 training dataset to 700 training dataset. As you can see, the naive Bayes once again beats out the rest of the classifiers as it has the least amount of time required. You can clearly see that because naive Bayes is a very simple classifier and is based on probabilistic theory, while the SVM has the most amount of time since it's a very complex classifier. The KNN comes in between the naive Bayes and the SVM in terms of time complexity. These were the following analyses I have made. The naive Bayes classifier has the best performance in terms of both accuracy and time complexity as well, while the nonlinear SVM was proved to be the one with the worst performance in terms of both accuracy and time complexity as well. As I've stated before, the accuracy of the linear SVM is almost the same as the naive Bayes if we have enough amount of training samples. Since we did not have more than 700 training samples, we could not evaluate the performance of the SVM for training samples of more than 1000 and see whether it beats the naive Bayes classifier. In conclusion, the naive Bayes classifier, although a very simple probabilistic classifier, has still proved to outperform most of the widely prevalent machine learning algorithms today when it comes to text-based classification, and still it is widely used and a popular choice for performing spam filtering. The naive Bayes classifier has been further modified today to effectively recognize more type of spam emails, and they have been further developed and built upon. Presently, the most effective models are still based on the naive Bayes model. These are the relative work to the project that I have created. Now, let us look at the MATLAB demonstration of this project.